Good evening, students. So we have thoroughly enjoyed the postulates of Bohr's model. We derived radius, we derived energy, we derived velocity, we derived Rydberg constant, we got the energy of a radiation, we know how to calculate the energy of a spectral line. In the yesterday test also we gave some good questions, we will discuss that also. And so we thoroughly got appreciated Niels Bohr's model. And what is the biggest advantage we enjoyed through Bohr's model was we had a clear-cut explanation of hydrogen spectrum. Like you take so many hydrogen atoms in a discharge tube, millions of atoms, where electrons get excited when you subject it to electric discharge, and when the electrons get de-excited, it can happen in stepwise manner and direct manner. There is a possibility for a large number of emission of photons, which would cause different series of spectral lines. Different series are formed in different regions, ultraviolet region, infrared region, we got invisible region like. And why there are different series formed in hydrogen atom? The only thing I advise the students to appreciate, the energy gap from first to second to third, fourth, fifth, like between successive orbits keep on decreasing. That is the most appreciable point what you should really highlight in Bohr's model. I have been telling you one thing right from the beginning. Be aware of the fact that between successive orbits, first to second, second to third, third to fourth, the physical distance increases. The distance between 2 and 3 is larger than 1 and 2. Whereas the energy gap between 1 and 2 is larger than 2 and 3 is larger than 3 and 4. It is like that. That we have already seen. See, in the so many times we discussed this. Suppose minus 13.6, minus 3.4 electron volts, minus 1.51, minus 0.85, and at infinite 0. If you take the energy gap between these two, 10.2, a big gap. If you take the energy gap between 0 to, infinity to second also, it is just 3.4. What a great interesting point. Between second and first itself is much larger compared to the rest of all the energy levels gap, bandwidth. See the beauty. So let anything happen inside, will release a photon of very less energy compared to 2 to 1. Of course, not only 2 to 1, 3 to 1, 4 to 1, 5 to 1, that all will be more than 10.2. Maximum is 13.6 if it is hydrogen atom. Always remember, once you take another single electron species, don't take helium, you have to take helium plus. In helium plus, it will be square effect, Z square effect. Multiply it with Z square. Instead of 10.2, it will be 10.2 into 4. 40.8 electron volt photon is released. Very high energy photon. So that need not be ultraviolet. Never be carried away by, higher to 2 should always be a visible line. It is in hydrogen atom, it is a visible line. We will appreciate all that in a, what should I say, visual. See this. See, from nth infinity level to first orbit, if electron jumps, that is the maximum gap, energy gap. 0 and energy value 0 to minus 13.6. This is minus 13.6 electron volts. This is 0 electron volt. What is the gap? This gap 13.6 electron volts per atom. Highest, and the corresponding wavelength will fall in ultraviolet region. Whereas if the electron is if it is jumping from 2 to 1, what will be the gap? Just now I told 2 is minus 3.4. Minus 3.4 to 13.6. Electron jumps. This gap is how much? 10.2 electron. These are all nice numbers. You should always be in contact. Whenever you have hydrogen atom, these are fixed numbers. You have to be very familiar with these numbers. You like it. So at 10.2 electron volts also, corresponding wavelength, if you can calculate Hc by lambda, that will be again ultraviolet light only. And this is the least energetic line. This is the most energetic line. And 2 to 1 itself is ultraviolet. 0 to infinity to 1 will also be ultraviolet here. So all the other transitions, 2 to 1, 3 to 1, 4 to 1, these are all corresponding to ultraviolet light. And there is a small language, 2 to 1, 3 to 1, 4 to 1, like that, infinity to 1. See how many varieties of lines you may find in the first series, highest energy series. And we call this series as Lyman series. There also some language, but this is the least energetic line, because electron is jumping from immediate highest state to higher state to ground state, and most energetic is infinity to 1, and infinity to 1, that is called series limiting line, most energetic line in a series. So this is called Lyman series. All lines are formed in ultraviolet, and all are not happening in a single hydrogen atom. Different hydrogen atoms may give different varieties of transitions, and you may have different photons released. So coming to the second series, see, this series will not be very energetic series. In different hydrogen atoms, electrons are jumping from 3 to 2, 4 to 2, 5 to 2, 3 to 2, 4 to 2, 5 to 2, infinity to 2. Which will be the most energetic line? Infinity to 2, least energetic 3 to 2. How to know the wavelength of a particular transition? Go for Rydberg equation. So you can calculate lambda, and based on that you can work out that these are all in visible region. The most energetic infinity to 2, the least energetic 3 to 2. All these lines will fall in visible region. If we calculate, we can easily understand that falls in visible region. So this series only you can see. Other series are not, you can't see in the visible region. And this is still narrowed. See, the gap is decreasing. Once the gap is coming so down, the photon will have very less energy. So wavelength will be very high. So you are getting infrared radiations. And even electron falls into the third state from 4th, 5th, 6th, infinity also. The energy gap is after all how much? This is minus 1.51. This is minus 0.85. This gap itself is 0 to 0.85. 0.85 electron volts. If you can correspondingly calculate the wavelength, it falls in infrared radiation, heat radiation, thermal radiations you will get. So this is what is hydrogen spectrum, grand success of Niels Bohr's model. Every line's energy we can calculate using Rydberg's equation. So let us see some visual. See this now. This is a hydrogen spectrum, Bohr series hydrogen spectrum. It's only one series because this is only visible. See, violet to red, and this line is Lyman series. How to calculate the energy of this line, energy of that line? How to calculate lambda? This is second orbit to first orbit transition. So we have got 1 by lambda is RH into 1 by n1 square minus 1 by n2 square. This is the best equation available to calculate the wavelength. So 1 by lambda is RH into 1 by 1 square minus 1 by 2 square. So this is going to give you RH into 1 minus 1 by 4. This gives you RH into 3 by 4, and lambda is equal to 4 by 3, 1 by RH, and 1 by RH is 912. So this goes 304 times. You are getting a wavelength of 1216 angstroms. 1216 angstroms definitely corresponds to ultraviolet light, below violet. And what could be the highest energy radiation? Infinite to 1. How will you calculate? 1 by lambda is equal to RH into 1 by 1 square minus 1 by infinity square. 1 by infinity square is 0. So this is 0. So implies lambda will be how much? Reciprocal of RH. So lambda is equal to 912 angstroms, still less wavelength. So 912 angstroms and 1216 angstroms is the limit of Lyman series. Lyman series ranges from 912 to 1216 angstroms, which is invisible. The most energetic is 912, less the wavelength, more the energy, more the wavelength, less the energy. So 2 to 1 least energetic line, and infinity to 1 the series limiting line, most energetic line. So my dear students, then go to Bohr. In Bohr series, electrons fall into second state, 3 to 2. The 3 to 2 is called H alpha line, and 4 to 2 is called H beta line, like that. 5 to 2 H gamma line, just like that. Then infrared. But one thing you always calculate, you can always use expressions like this to calculate the wavelength. So coming to, of course, naming the names and regions. You have Lyman series when electrons fall into first orbit, that is in ultraviolet region, and Bohr electrons fall into second, and Paschen when electrons fall into third, fourth, fifth, the bracket, Fund and Humphrey, and you have got the regions. Lyman series formed in ultraviolet, visible, near infra, far infra, like that. Very simple to understand now Bohr's model. I mean hydrogen spectrum with reference to Niels Bohr's model. But dear students, you don't forget one thing very clearly. There are plenty number of atoms, like big, huge number of atoms where transitions are happening. So we are statistically taking all the transitions are taking place. But very few atoms are there, it is practically not possible. You can't get a spectrum like. So you will have large number of atoms, almost all kind of transitions will take place, stepwise transitions and in between two lines and all. How to calculate how many lines you may get in one particular series and all, we will have a brief discussion. Now just see, appreciate this beautiful set of spectra. As I told you, every element will give its own unique spectrum, because based on spectrum is an impression of radiations that come from an atom, excited atom, if it is emission spectrum. So every atom has got its own internal structure. That is what we are struggling to understand. So in that particular spectrum, different atoms will have different atomic structures. So the transitions, limitations, and whatever is there, conditions, boundary conditions, and quantizations, everything will influence the formation of spectral lines. So each different atoms will give different variety of spectra. See hydrogen spectrum. See you have got visible spectrum. This is only Bohr series shown there. Helium spectrum has got some other kind of thing. This is not a single electron spectrum, multi-electron spectra. And what about neon? See, it is giving some other pattern. The sodium, you have got only two lines, bright yellow lights, 5890, 5896. And mercury spectrum has got some other lines. But one thing you all remember, all these lines cannot be explained by Bohr. Bohr could explain only hydrogen spectrum. It is an advantage and you can tell the disadvantage also. What is the advantage of Bohr's model? We could verify the value of RH. Rydberg constant was earlier proposed by Rydberg before Bohr's model came. To calculate the spectral lines in that hydrogen atom, he cut the rhythm and got here RH. And that RH was practically verified with us mathematically with the help of the energy expressions and all what we have done in the previous class. So RH value 109677 some odd decimal point centimeter inverse was successfully verified by Niels Bohr's model. That's the biggest advantage, and this is another big advantage of Bohr's model. First time a successful model to explain the discrete nature of spectrum. Why discrete? Electron jumps from quantized orbits from one orbit to other orbit. There is a clear difference in the energy, so you will get the spectral line very special, discrete in nature. Two spectral lines do not merge. They will be clearly differing in their wavelengths based on the transition nature. So what I would like to suggest here, Bohr's model grants access for single electron species, hydrogen, helium plus, lithium plus 2. What happens in helium plus? The lines would shift, that's it. Again, there also you will have a number of series of spectral lines, but it would shift. That is because wavelengths will not be same, because there is a Z square in RH expression, Rydberg equation. RH into Z square is there. Based on that, the energy would differ from hydrogen to helium plus 2, lithium plus 2 to beryllium plus 3. So, but pattern of spectral lines and all is discrete and the regions would differ. As you see visible region, you have got Balmer series in hydrogen atom. For same transitions, don't think you will get visible light only in lithium and other spectra, because you are multiplying with Z square. The energy which caused the spectral line is multiplied with 9, 3 square in lithium. Why will it form the spectral line there? It will form somewhere in maybe ultraviolet, maybe X-rays, we don't know. We have to calculate and check. Anyhow, that's a very good success about Niels Bohr's model, hydrogen spectrum. Hydrogen like single electron species spectra he could successfully explain, and he verified RH value, like we got energy, principal energy of an electron, perfect calculation, principal energy state, distance from the nucleus, everything is perfect. But there are drawbacks in Niels Bohr's model. What are those drawbacks? Actually, Niels Bohr's model, first thing, it may look silly, he never spoke about the sphere-like atom. He said orbits. So there will be orbit, electron, it is almost giving a two-dimensional view, not a 3D view. That's not a very big objection. Second objection is limitation you can say. Suppose you have taken a spectrum. Suppose you take some sodium spectrum you have taken, or whatever, some mercury spectrum, you have hydrogen, different spectra we have seen. But if the sample is kept in a strong magnetic field, very strong magnetic field, if you keep the sample and then obtain the spectrum, instead of one line, you will have many lines formed. Suppose this is without magnetic field, suppose you are getting a single line. See, this is without magnetic field, but this is with magnetic field. The sample is not exposed to any magnetic field, but here is a sample is subjected to a magnetic field. I am not taking a mixer, don't think. I am taking any sample, atomic sample. If I obtain the spectrum by subjecting the sample to a magnetic field, instead of one line, you are getting a group of lines. Means there are further smaller transitions taking place. And Bohr had no answer, because as per Bohr's theory, electronic transitions are orbit to orbit. So how can there will be many transitions within the orbit? No answer from Niels Bohr. Not only magnetic field, this effect is called Zeeman effect. If similar thing happens in electric field, and this is called Stark effect. So if you subject the sample to magnetic field and obtain the spectrum, a group of lines are formed. If you subject the sample to electric field, a group of lines are formed. So go and ask Bohr's model and you can't get any answer, proper answer. So it's a limitation. We don't call it a defect. Bohr's model could not be, extended to explain Zeeman and Stark effects. That is another disadvantage, or whatever you say, limitation of Niels Bohr's model. And one more big objection in Niels Bohr's model is uncertainty. Like it contradicts uncertainty. There is in future, in next few classes, we are going to discuss about Heisenberg's principle. A widely accepted principle called uncertainty principle. Uncertainty principle, widely accepted. As per that, it is not possible to locate an electron in one particular point along with its momentum or velocity. Not possible. Impossible to locate an electron, just like how you locate in an orbit. In an orbit, electron is at a fixed distance from the nucleus. As per uncertainty principle given by Heisenberg, it is not like that. Then you may say, who says that may be wrong, this Bohr may be correct. No, it is widely acceptable, and we have got better scientific advancements what we have got in quantum physics. So Bohr's model is in contradiction with this. It doesn't match like. So what are the objections of Bohr's model? Bohr's model cannot explain multi-electronic spectra. That sodium spectrum, mercury spectrum you have seen, no? You can't explain those spectra. These spectra cannot be explained by, Bohr's model. Only this can be explained, or helium plus, lithium plus. Single electron spectra, Bohr's model can explain. And whatever equations we have derived, minus 2 pi square mz square e power 4 by n square h square, energy of electron, 2 pi square mz square e power 4 by h cube c Rydberg constant, and all. These are all meant only for the systems containing one nucleus and one electron alone. All these expressions you can't use for sodium spectrum and all. So Bohr's model fails to explain these. So advantage is that, disadvantage is also that, and it contradicts Heisenberg's widely acceptable Heisenberg's uncertainty principle. And so this is how we can say we have thoroughly done with Bohr's model. Lot to do, but still I am not much contented unless I expose my students to some good number of questions and how to handle such questions. While learning those questions also, I think you will get better picture on Niels Bohr's model and other small concepts supporting Bohr's model. We will go into that exercise. So that's it, my students. So which species has least energetic ground state electron? 4 species are given: hydrogen, and you have helium plus, you have lithium plus 2, and you have beryllium plus 3. See try to understand the question very clearly. Least energetic ground state electron. Ground state means what? Every electron in its least possible state is called their respective ground states. This is the ground state of this, this is the ground state of this. That means what? First orbit, first orbit, first orbit, first orbit. Now, among these 4, which has got least energy? And we have done so much with Bohr's model. Energy of electron in the first Bohr's orbit we have done. Minus 13.6 z square by n square is the general expression. And n square, first orbit means n is 1. So minus 13.6 z square. For hydrogen, z is 1. So what is the energy of this electron? Minus 13.6 electron volts. What about this electron? For this, z is not 1, z is 2. So minus 13.6 2 square. What is the energy of this electron? Minus 13.6 3 square. What is the energy of this? Minus 13.6 into 4 square. Now see the symbol minus is there. So that is the most negative energy. The other day while teaching the physical meaning of energy of an electron, I clearly mentioned what? Energy of electron is expressed in negative. Why there is a negative sign? Because electron is coming from a free state to it's entering into the influence of an atom. It starts getting attracted towards the nucleus, and deeper it enters into the atom. It goes closer and closer to the nucleus, and it loses more and more energy. The more energy is lost due to attraction. So more negative value means more it is attracted, or vice versa. More the electron is attracted, more the negative value it is, and least the energy of that electron. Because why there is a negative value? Because it has lost energy from 0 and entering into the nuclear influence, losing more energy to form this state. So this has got least energy. Most minus, so least energy. So in the infinite state, everybody will have 0. You take that electron into infinite, all the electrons will have 0 energy. So from 0 only they lost so much. Which electron has lost more energy? This electron has lost more energy. So its energy is minus 13.6 into 4 square, 16. So that electron has least energy. So be careful. It's a very interesting thing. And which species has electron in the maximum kinetic energy in the ground state? This time the question is about kinetic energy. See why these questions are framed? Just to make you understand the physical meaning of electron. So this is hydrogen, helium plus, lithium plus 2, beryllium plus 3 or 3 plus whatever. So all have electron. What relation I gave the other day? Kinetic energy, just change the sign of the total energy. So minus 13.6 is total energy, 13.6 is kinetic energy. What is the kinetic energy of this electron? 13.6 Z square means 2 square. Here 13.6 3 square, 13.6 4 square. Now do you have that minus symbol, minus sign before the energy? No. Now these are all positive values. 13.6 into 4, 9 and 16. So these are positive values. Which positive value is highest? 13.6 into 4 square. The question is about kinetic energy. So the greater the nuclear power, the electron will have greater kinetic energy provided all orbits are same. Z square times Z is more, kinetic energy is more. So that is the beauty of this question. See, potential energy is least, total energy is least, but kinetic energy is highest. For that, as Z increases, potential energy drops, total energy drops, kinetic energy will rise. So this has got highest kinetic energy. To cancel this nuclear attraction, it has to revolve around the nucleus at a faster rate, like that. This is yet another lovely observation about the radiations, photons and all. See, transitions between 2 and 1. What is the question? Highest energy photon we want. In which case, highest energy photon is released. See, 2 to 1, 3 to 2, both in hydrogen only. Just now I explained. The energy gap decreases as you move away from the nucleus between two successive orbits. 2 to 1 gap is pretty high, 3 to 2 gap is less. So more the gap, more energy photon is released. This gap is more, this gap is less. Energy gap, I mean to say. This is minus 13.6 and minus 3.4. What is the gap? 10.2. This is minus 1.51. What is the gap? 1.9. So as the 2 to 1, 10.2 gap, See, these are all very dear numbers, very dear numbers. It's a universal fact. One must, get accustomed to these values. Not that I am telling you to by heart kind of a thing. You like them. You get familiarized to these numbers. These are very unique numbers. We got them from Niels Bohr's atomic model, and they are fixed. You are not newly calculating anything. So always 2 to 1 transition gives a better photon, larger, high energy photon. That is one way of saying. And we know this gives ultraviolet photon, and that gives visible photon. We have calculated. And this is, Lyman series, and this is Balmer series. So this will give a better photon than this. So always 2 to 1 is better than 3 to 2 in energy. Be careful. If wavelength is asked, the reverse. This wavelength will be less, this wavelength will be more. And now 2 to 1 in helium plus 3 to 2 in helium. There also 2 to 1 is better. So definitely this is better. So in these two, which is better? In which case high energy photon is released. See, remember we have an expression E is equal to 13.6 Z square into 1 by N1 square minus 1 by N2 square. Now we are comparing 2 to 1 only in both hydrogen atom and helium plus. So once these two are same, so now what matters this energy? Z. For hydrogen Z is 1, for helium Z is 2. So there the energy released is more. That's a stronger a photon that comes. A more energetic photon is released in helium transition because Z square times. So hydrogen, helium plus, lithium plus 2, beryllium plus 3, if you want to compare anything, if the transition is fixed, Z square will influence the energy, frequency and wave number. More the Z, more the energy, more the frequency, more the wave number, less the wavelength, because lambda and energy will be in inverse relation. So what could be the answer? Highest energy, 2 to 1 in helium plus. What is the ratio of wavelengths of first and last line of Balmer series? What do you mean by first and last line? In any series there will be a limit. Balmer means the lower limit is what? 2. For Lyman lower limit is 1. For Balmer lower limit is 2. For Passion lower limit is 3. Based on lower limit only we decide the name of the series. So in Balmer the lower limit is 2. So what could be the transitions? 3 to 2, 4 to 2, 5 to 2 goes on infinity to 2. And this is the last line. There cannot be more than infinity. So for every series there are limits. This is least energetic. This is highest energy. Any series limiting line has maximum energy, maximum frequency, minimum wavelength. So my dear students, he is asking what is the ratio of wavelengths of these two. So let us work out 3 to 2 transition, infinity to 2 transition. So 1 by lambda is equal to infinity to 2. Let us go for 3 to 2 first. RH into 1 by 2 square minus 1 by 3 square. This gives me RH into 1 by 4 minus 1 by 9. 36 is LCM. 5 by 36. 1 by lambda. And we call it lambda 1. 1 by lambda 2. RH into 2 square is lower level is same. Higher level is infinity. So you are going to get RH into this is 0 into 1 by 4. When you take the ratio of these two, lambda 2 by lambda 1 will be, this get cancelled and this is going to be 5 by 36 into 4 by 1. This goes 9. I took the reverse ratio, so 5. Any ratio will do. Very simple. But only recognize least energy radiation and highest energy radiation in any series. See, this is about the energy of most energetic Balmer line is X. What is least energetic Lyman line? Now this time series is also changed, but both are happening in hydrogen atom only. Most energetic Balmer line, least energetic Lyman line. Such description only you should be very clear. Most energetic Balmer line means what? Within Balmer series, most energetic is always infinity to 2. Most energetic means infinity, Balmer means 2. Least energetic Lyman means 1. Least energetic, don't go for infinity, go for 2. So infinity to 2, 2 to 1. And he is asking the ratio of the energy ratio. So how to calculate energy? Lambda is equal, sorry. Energy of the transition is 13.6 into, both are in hydrogen atom, 1 by 2 square minus 1 by infinity square. Have you observed something? When I said energy, I am going for 13.6 into Z square. When I want wavelength, I should go for Rydberg equation, Rydberg constant. So now again energy is equal to 13.6, because it is hydrogen, Z is 1, this will be 1 by 1 square minus 1 by 2 square. And this is going to be 4, 1 by 4, this is going to be 3 by 4, 1 minus 1 by 4, 3 by 4. So E1 by E2, I'll call it E1, I'll call it E2, 13.6 get cancelled, and I am going to get 1 by 4 by 3 by 4 means 1 by 3. And this E1 is given as how much? X. So E2 will be 3x. E2 will be 3x. So simply energy calculations we are working out. See, I just told you the physical meaning of the distances and energies. He is asking about that only. The physical distance between two successive orbits D1, D2, D3. As I told you, the distance keeps on increasing. The correct way of drawing Bohr's model, is this correct, or is this correct, or is this correct? Which one is correct? Which one is correct? See here what is happening, the gaps are identical. If this is x, this is also x. Here this gap is less, this gap is more, this gap is still more. Gap is increasing between two successive orbits. Here what is happening? First gap is so big, second gap is so narrow. So this is wrong, this is wrong, this is correct. The physical spacing between two successive orbits keep on increasing. So D1 is less than D2 is a correct statement. D1 is equal to D2 is a wrong statement. What about energy gap? Energy gap keeps on decreasing. See, this will be greater than this. So this A and D are correct. Which transition in helium plus gives similar spectral line as the least energetic Lyman line in hydrogen atom, hydrogen spectrum? What do you mean by least energetic Lyman line in hydrogen spectrum? Lyman, it must be 1. Least energetic, 2 to 1. Be careful, least energetic means 2 to 1, most energetic means infinity to 1. So you have got 2 to 1 happening in hydrogen. Let us first calculate the energy. Whatever wavelength or energy, no problem. Energy is 13.6 into hydrogen 1 square into 1 by 1 square minus 1 by 2 square. That is the energy. And we want similar energy even in helium. We don't know the transition. So E is equal to 13.6 into 2 square, because it is helium plus, atomic number 2 into 1 by n1 square minus 1 by n2 square. He is asking which transition helium plus gives similar spectral line. He did not even mention one of the orbits. Both orbits we do not know, and we want these two energies to be same. So, what can I equalize? 13.6 into 1 by 4, 1 minus 1 by 4, 3 by 4 is equal to 13.6 into z square 4, 1 by n1 square minus 1 by n2 square. This get cancelled. You are getting 3 by 16 if you observe carefully. So, 1 by n1 square minus 1 by n2 square. See, once you have 16 here, these being quantized values, which square can be, what should I say, 16, 4 square. So, definitely this is 4. So, from that you can calculate n1, you will get 2. So, 4 to 2 transition. So, 2 to 1 in hydrogen, 2 to 1 in hydrogen, 4 to 2 in helium plus give identical wavelengths. You can write Rydberg equation and verify that, you will find it true. That is a beautiful question. Suppose I say at this particular juncture I have got some thought. Suppose I have got electron in 4th orbit in hydrogen and electron in 4th orbit in helium plus 1, 2, 3, 4. This is helium plus. When they are falling, how many spectral lines may be formed? Of course, you have got so many atoms. In all those atoms, you have got electrons in the 4th. So, there can be what kind of transitions here? 4 to 1, 4 to 3, 4 to 2, yeah, and 3 to 1, many transitions will take place. So, how many spectral lines? Here what I would like to tell, or I can, while counting the number of spectral lines, suppose if 2 to 1 is there, here 4 to 2 is there, do not count them as different transitions, both of them are same. Because in 2 to 1 whatever energy is released, just now we have calculated, in 4 to 2 in helium also same energy is released. In 2 to 1 how much energy is released? 13.6 into 1 by 1 square minus 1 by 2 square. That is 13.6 into 1 by 3 by 4. Whereas in the second case 13.6 into 4 helium into 1 by 2 square minus 1 by 4 square. LCM is 16. 13.6 into 4 into LCM is 16. 4 minus 1, 3. So, this goes 4 times, 3 by 4, 3 by 4. So, while counting the number of spectral lines, do not count them separately. They both belong to same energy, same photon. They intensify the line in the spectrum, but it will not be a different spectrum. The same discharge tube contains both hydrogen and helium plus. Do not take them as two different transitions. They both give similar photon, ultraviolet photon only. See 4 to 2 in helium, because it is into 2, do not think it is Balmer series, do not think it is going to give you a visible light. There also it is ultraviolet light. Ionization potential of hydrogen atom is x electron volts. What is the third IP of lithium? So, first of all, what is ionization potential of any species? 13.6 Z square. Any species ionization potential is 13.6 Z square electron volts per atom. Why like that? As I told you, the orbit's energy here minus 13.6 Z square. How to make it 0? If it is 0 only, we call it ionization potential. How to make this value as 0? Add 13.6 Z square electron volts. 13.6 Z square is IP. So Z is what? 1 for hydrogen. So ionization potential of hydrogen is 13.6. Ionization potential 3 of lithium means what? Ionization potential 3 of lithium means what? Lithium's first IP is this. We can't calculate. We cannot calculate the first IP of lithium because it is not a single electron species. We don't have equations for that. I mean mathematically. So lithium plus 2, second electron loss. We can't calculate. Lithium plus 2, lithium plus 3 we can calculate. Why? Because this is a single electron species. For a single electron species, what is the ionization potential? 13.6 into Z square. And this is what? IP1, IP2, IP3 of lithium. So third IP of lithium is nothing but IP of lithium plus 2. So this will be how much? 13.6 into 3 square. So when this is called as X, this will be X, 9X. Ionization potential of lithium plus 2 is 9 times more than that of hydrogen because of Z square. The wavelength of 2 to 1 transition in H atom is X angstroms. What is the wavelength of 2 to 1 transition in lithium 2 plus? Simple logic. Just don't do any calculation, try to work out. Lithium plus 2 transition will be more energetic transition or less energetic transition. It is only 2 to 1 transition in both cases. So the 2 to 1 transition in hydrogen, 2 to 1 transition in lithium plus 2. In lithium plus 2, the energy will be 9 times more because Z square 9 times more. But he is asking wavelength. Wavelength is inverse relation. So it will be X by 9. 2 to 1. Simple things you have to conclude like that. Otherwise you have to go for 1 by lambda in hydrogen is equal to Rydberg constant into 1 square into 1 by 1 square minus 1 by 2 square. Again 1 by lambda in lithium plus 2 is equal to RH into 3 square excuse me 1 square minus 1 by 2 square. And again you divide, cancel that, then this by this will be again 9. One is X, the other one will be X by 9. You will get a shorter wavelength because energy is more in lithium plus 2. Like that. What is the energy of electron in H atom in X ground state? The potential energy of electron in hydrogen atom in ground state is X. What is its kinetic energy? He gave potential energy. He is asking kinetic energy. And I gave 3 very important relations what we got from Bohr's model. Potential energy is always 2 times the total energy. Kinetic energy is always what? Minus of total energy. Now he gave potential energy. How much potential energy he gave? X. Means this is X. So what is total energy? X by 2. So once total energy is X by 2, kinetic energy will be minus X by 2. So don't think kinetic energy, how can it be negative? Because X value itself is negative. Because it's potential energy. This value includes negative. Minus of minus plus half. These relations are very essential. How much energy is required to knock out an electron from first excited state of H atom? See, hydrogen atom is here. Here minus 13.6. Minus 13.6 by 2 square. Minus 3.4 electron volts. This is infinity, 0. I want to take out the electron from first orbit, I should make it 0. If I want to take out electron from second orbit, I should make the energy 0. So to make the energy 0 from here, I need to add 13.6 electron volts. To make this energy 0, I need to add just 3.4 electron volts. So the answer is 3.4. Energy required to knock out an electron always means just make the energy 0. How to make the energy 0? There will be a negative energy, give the positive value for that. Suppose how to knock out an electron from the first excited state in helium plus. So obviously Z square, 3.6 into 2 square, that much energy would be required. The kinetic energy of electron in ground state is X. What is the potential energy of ground state electron in helium plus? Now he changed species and he changed the type of energies also. So the kinetic energy of electron in ground state H atom, in H atom, what is kinetic energy? Minus of total energy, so 13.6. In hydrogen atom, he is asking potential energy of ground state in lithium plus. So what is now we just calculate kinetic energy of lithium plus 2 in ground state will be obviously Z square of this, no? So 13.6 into 2 square. This is kinetic energy. What is the total energy? Lithium plus 2, negative of this. What is the potential energy of helium plus lithium plus 2? Double of this, minus 13.6 into 2 square into 2. So I can write it 2 cube. And this is kinetic energy. This is potential energy of lithium. Now we should take the ratio of this. So X by potential energy of lithium plus 2 electron is equal to 13.6 by 13.6 into 8 minus. So 13.6 get cancelled. So potential energy of lithium plus 2 electron minus 8x. Just do like this, compare like this. How many spectral lines may be expected? Bohr series in the electron in H atoms excited in 6th orbits. Bohr series only he wants. So electrons are excited into 6th orbit. So let us physically calculate 1, 2, 3, 4, 5, 6. All these incidents are not happening in the same atom. Large number of atoms are there. We want only Bohr series. In some hydrogen atoms, maybe 6 to 2 take place. Some other hydrogen atoms 5 to 2 take place. Some other hydrogen atom 4 to 2. Some other hydrogen atom 3 to 2. From wherever, if electron jumps into second orbit, you will get a Bohr line. So these are the 4 possible transitions in large number of atoms that may take place. So maximum you will get 4 lines. First of all, in any species, if you take hydrogen, number of Lyman lines from any higher state will be n higher minus 1. Suppose 5th to 1, 5 to 1, 4 to 1, 3 to 1, 2 to 1, like that. So n Bohr lines will be always n higher minus 2, like that. So 6 minus 2, 4 Bohr lines you will get. But it is not like that. Only Bohr line you are asking. You are excluding Lyman, you are excluding Paschen and all. If you want all spectral lines, how to work out? Number of spectral lines between N2 and N1. Between two limits N2 and N1, how many spectral lines altogether may be possible? So first you go for an X which is N2 minus N1. Take the difference between the principal quantum numbers involved, a number of spectral lines, all spectral lines is equal to X into X plus 1 by 2. This is statistically you can work out, very simple. Suppose 6th orbits, this is okay. He is only taking Balmer lines. We want all lines together. Suppose between 6 and 2, what are all the possible lines? Let it be Balmer, let it be Paschen. There is no possibility for Lyman because the lower limit is 2. If you want exclusive Balmer lines, 6 minus 2. If you want total lines, spectral lines, what is the difference between 6 and 2? 4. So 4 into 4 plus 1 by 2. There will be 10 lines formed. 10 lines, all together lines. This is how we calculate. What is the wavelength of most energetic spectral line in the Lyman series of H atom? Lyman 2 to 1, 3 to 1, infinity to 1. Most energetic, infinity to 1. He wants what? Wavelength. So 1 by lambda is equal to RH into 1 by 1 square minus 1 by infinity square. 1 by infinity square is 0. So this is simply RH. So lambda is equal to 1 by RH. This is going to give you 912 angstroms. Most energetic line wavelength. An indigo spectral line may be formed in hydrogen spectrum due to which transition? Indigo is a visible color. Visible light is only formed in Balmer series. In Balmer series, the lowest state is 2. So 2 to 1 ultraviolet, UV, infrared, again UV, this is visible. Indigo is visible. So we will get a Balmer line. What is the stopping potential of the photoelectric effect he is asking about? And I mentioned during photoelectric effect, electron is ejected. If you want electron to not to come out, you need to apply a potential reverse to it. And I also tell, because it is electron, the kinetic energy of the ejected electron will numerically be equal to, in electron volts, will be numerically equal to the stopping potential. So simple logic. So this metal has got 3 electron volts work function, and this photon is having 3000 angstroms wavelength. So first calculate kinetic energy, but this is wavelength given, this is energy given. So calculate the energy of the incident photon. Once you know wavelength, you must be able to calculate energy. So energy is equal to Hc by lambda. H is 6.63 into 10 power minus 34 into velocity 3 into 10 power 10 centimeters, 8 meters, by lambda is given as 3000 angstroms into 10 to the power of minus 10 meters. So 3 zeros, this will give 10 power 15, 10 power 15 and 10 power minus 34, 10 power minus 19. So 3 and 3 get cancelled. 6.63 into 10 power minus 19 joules. I want it in electron volts. How to convert? Divided by 1.6 into 10 power minus 19. So this and this get cancelled. I will get 4.1 electron volts. So 4.1 electron volts is the energy of the incident photon, out of which 3 electron volts is absorbed by the metal as its work function, and the difference will be converted into kinetic energy of photoelectric electron. So it will be 1.1 is electron volts is the kinetic energy of the photoelectron, but stopping potential will be just this numerical value only, but in volts. So 1.1 volts. So my dear students, we have thoroughly enjoyed how to calculate number of spectral lines and energy of every spectral line, wavelength of a spectral line in different species, different orbit, between different orbits, what could be the energy, everything you can calculate just with simple 3-4 expressions and 3-4 relations. So we will still enjoy some more discussion on Bohr's workouts, and then we will switch over to de Broglie's concept, which opens a new gate, as I told you, to quantum mechanics. Have a good day, enjoy.